to thank the local organizing committee for inviting me here. I'm very honored to be here, and it's a pleasure. I'm going to try, as they say, to tie into the theme of this conference, One Environment, One Health, Sustainable Societies, by talking about One Health, persistent organic pollutants, and the Arctic. And One Health is based on a recognition that the health of humans, animals, and ecosystems, and the entire planet are all interconnected. And it applies cross-disciplinary approaches to address the risks across this entire interface. And this has been done for disease vectors before, and now is being used for contaminants. And I want to illustrate how the Arctic has been a bellwether or an early warning system for planetary health in a range of different contaminant issues, but particularly for the persistent organic pollutants. So first, just for those of you who are not aware of what the Arctic is, I mean, it's more than just the Arctic Ocean. It's the 8 countries that have territory in the areas above the Arctic Circle, and this is Russia, Finland, Sweden, Norway, Iceland, Denmark, represented by Greenland, Canada, and the US, represented by Alaska. Let's see here. So as I said, I'm going to do this using persistent organic pollutants, and I'm going to use PCB and the history of PCB in the Arctic as an illustration here. So in the 60s, the late 60s, PCBs were first identified in Baltic Sea biota. And then in the 70s, there were Canadian scientists who started to find PCB in marine mammals and fish, seals and polar bears, for instance, in the high Arctic of Canada. And this is a pristine environment. So this was, of course, a question mark. How were these PCBs getting there? And there were no, at least at that time, known local sources that they could come up with. But later on, they began to wonder about what are called the defense early warning sites. And this was a pearl band of military radar stations following the Arctic Circle from Alaska to the east parts of the Arctic Canada. And these were there to warn of potential Russian nuclear missiles that might be coming over the Arctic Circle and heading for North America. And these were closed down in the 60s and 70s and abandoned, essentially, with everything left there, including all the electronics and electrical equipment that contained PCBs. And so there was a worry that maybe this could be the source of these PCBs, but they found when they studied this that the PCBs were actually quite locally contained, so they weren't found more than 20 kilometers outside of the where these sites were. The fact that they had found PCBs in marine mammals and fish was a worrisome problem for a lot of the indigenous populations because this is their food. And so they were becoming concerned what this might mean for them. So there were some sampling campaigns that were started in, I don't seem to have a pointer. Oh, there it is, very tiny. They had sampling campaigns then in 2 spots, Broughton Island, they took blood samples and some food items, and in Nunavut here in northern Quebec and in southern Quebec in Quebec City. They took samples from the Inuit in the northern Quebec and in Broughton Island, and then in Caucasians in southern Quebec. And the breast milk samples then. And the findings were rather surprising. They found rather high PCB levels in the plasma of some of the Broughton Island Inuit, not all of them, but some of them, and also in some of the food they were eating. And they found surprisingly high PCB levels in the breast milk of the northern Quebec Inuit compared to the Caucasians from the southern Quebec. And these were considered at that time to be among the highest PCB levels ever reported. So again, this raised questions. These PCBs were being found in Canada, but what about the rest of the Arctic? And so at this point, Russia was opening up, and it made it possible to begin some collaborations. So the 8 Arctic countries started to talk to each other about some sort of collaboration around environment. And they created the Arctic Environment Protection Strategy in 1991. And this is now called the Arctic Council. And these 8 countries signed this agreement here in Sweden, or in Finland, Rovaniemi, up in the north. And they created some task forces to help do this work for them. And one of them was formed in '93, is the Arctic Monitoring and Assessment Program. And AMAP then created a working group, and the working group was made up of representatives from all 8 of these countries, and it also included the Indigenous peoples organizations, which is the first. They'd never been represented in these kinds of international groups before. And they saw this immediate need to do some sort of overall assessment of the environment in the Arctic. And so they called scientists together to begin this process in 1994. That's where I got involved in the POPs expert group. And they created these expert groups, one for POPs, one for heavy metals, one for radioactivity, et cetera, and asked them to search the literature, compile all the information that was available, find monitoring data that was being compiled that wasn't published yet, and also research that was being done, and put this all together into a synthesis of what was happening in the circumpolar Arctic, not just each country, but in the whole Arctic. And this resulted in a report that was put in 2 different versions. There was a popular science version, and this was written mainly for the policymakers. And then there was the scientific version, which we call the brick because it weighs 5 kilos, and it's about that thick. And it has chapters on POPs, and heavy metals, radioactivity, acidifying substances, pHs, climate change, ozone, and UV, before this was ever actually a question, the big question it is today, and also on human health. So from this, I will extract a little bit of information then. So PCBs. So what did they find about PCBs? And this is PCBs in ringed seals. And the interesting first thing to notice is it was found everywhere they looked, in all of the ring seal populations they looked at. So PCBs was not just Canada. It was all over the Arctic. So it was all over these pristine areas. The second thing that was very interesting was that there was a spatial trend with higher levels on East Greenland and Svalbard and up in the Russian Barents area. So the Barents Sea here had the highest levels. And when they looked at polar bear, which eat ring seals, the levels were even higher. And now we have a kind of a better representation in Russia. And again, it was the higher levels in this Barents Sea area, East Greenland, Svalbard, and up over into the Russian Arctic. And the Human Health Group had samples of blood taken in indigenous populations across the Arctic. And they saw a similar pattern. They found PCB everywhere, and highest levels were on East Greenland. And here are the 2 populations that were studied in the beginning, the 2, Broughton Island and northern Quebec. So you have these even higher levels on East Greenland and also on the Faroe Islands. So how were these PCBs getting to the Arctic, and why were they in such high concentrations? Well, there were also scientists who were working on the pathways and transport of these and sources of these chemicals. And in this example, Knut Breivik at NILU had put together an inventory of where PCBs were used globally. And most of it was used in Eastern North America, in Western Europe, and in Japan. And so when they were looking at the air currents coming up from the southerly latitudes into the Arctic, the interesting point was that they were going right over these source regions for PCBs into the Barents Sea. And this was the explanation for why concentrations of PCB were so much higher in the Barents Sea area. But we also know that there are other properties that seem to play a role, and volatility is one of them. And Frank Vanya and Don Mackay presented their results on understanding this as well. And what they could show is that if you have a very high volatility chemical, it will fly. So they call them the flyers. So they'll fly and they might not even make it to the poles. And then you have some that are a little less volatile, and they will possibly hop from the warm emission area where they're evaporating, and when they hit the cold air in the Arctic, they condense out. And the relatively low volatility compounds like DDT and PCB may have to hop several times, evaporating when it's warm, and then they condense when it's cold. So they're called the multi-hoppers. And then we have some that we call hitchhikers because we think they're coming, well, we know that they're coming up to the Arctic on particles. So they're following with the particle because they aren't volatile enough. So this explained how the PCBs were getting to the Arctic. So why were they at such high concentrations? Well, that was because of the Arctic food web. And in the Arctic, it's cold and it's dark a lot of the year. So animals have to put on a lot of fat as an energy source, or they have to use a lot of fat. And interestingly, zooplankton and invertebrates in the Arctic actually have a higher fat content than in southerly latitudes. So that means these fat-soluble chemicals have more fat to dissolve in. So they can actually concentrate more chemical in their bodies than in southerly latitudes. And then it's a long food web. You have invertebrates, you have the zooplankton invertebrates, and then they're eaten by fish, and the fish are eaten by marine mammals and seabirds. And our friends, the polar bear and humans, are the tertiary predators. And this is a very long food chain compared to terrestrial food chains, which are basically grass, herbivore, predator. So you've got 3. Here you've got up to 6 different levels. And this leads to very high biomagnification. So you can get 16 billion times higher concentrations from a seawater to a polar bear for PCBs. And it's about 1,000 times if you just go from zooplankton. So you can get these really long food webs that biomagnify. So was there concern from these high levels? Well, yeah, but there was no evidence yet. All we knew was that really high levels of PCBs could cause effects in Baltic biota, such as ring seals. Oops, where'd we go? Sorry, hit the wrong button. So for ring seal and harbor seals in the Baltic, PCB was causing reproductive effects and effects on the immune system. And the effects thresholds then were compared to the concentration ranges in the Arctic biota, and you can see for seals, whales, polar bears, and Arctic fox that some of the populations do have levels that are high enough to be of concern for these kinds of effects. For humans, the Inuit populations, the 2 populations in the Canadian Arctic and the Greenland Inuit all had levels that are over a level of concern that Health Canada has. So again, a little bit worrisome. Also, because the high levels in the marine mammals, the tolerable daily intakes for PCBs were being exceeded for Inuit populations. And these levels now in some of the human and animal populations were considered to put them at risk for effects. But there were very few biomarker studies available at that time to confirm if any of this was happening, except for some indications of higher infection rates in Inuit children with the high PCB levels. Now, this is a very concerning thing for the people who are in the Arctic who are dependent on these food sources. these are what we call traditional foods or country foods. And for them, these are the fish and birds and mammals that they go out and hunt and catch locally. They're culturally very important, and they're important for both spiritual, social, and physical well-being for them. They see themselves as being what we eat. And this also is very important for holding communities together, because it's like a gel. A lot of these communities use the hunting as a community. It's either a community hunting or it's a community sharing process. And this is very, very intricate, but it's used to keep the, in a sense, to keep the society together. And these populations and groups have been sustainable societies previously for thousands of years. This is a way of life that they have been able to live on, and so on. So now, of course, it was compromised because there were suddenly high contaminant levels, and these were contaminants coming from somewhere completely else. It wasn't them they weren't using these contaminants. Someone else was using them. They were ending up in their food. So this has created something we call the Arctic dilemma. These country foods are important for the human health. They contain essential nutrients and vitamins and minerals. These people don't need to eat citrus fruits because they get their vitamin C from the animals they're eating, for instance. And the foods they're eating also show that are good for them in terms of lower rates of heart disease and lower diabetes rates. Breastfeeding, we know, is very important for infants. It strengthens their immune system. It increases mother-child bonding. And yet these high contaminant concentrations in their country food and in the breast milk might be affecting their health negatively. So their food is good for them, but it might not be so good for them. And this then becomes a big problem. And store-bought food, there were some populations that were going over to store-bought food more and more, and they were seeing higher risks of heart disease and diabetes in these groups. So it's kind of a damned if you do, damned if you don't situation. So the results for this first AMAP report had a major impact because they were showing these high population or high POP concentrations in top predators and humans, much higher than in southerly latitudes. Long-range atmospheric transport was playing a role. The long food webs and fat as an important nutritional source were leading to high biomagnification of this. And these levels could be as high enough to be causing effects in animals and humans. So this was a public health issue as well. And the global community reacted and decided to do something about this. And this is when the creation of the UN Stockholm Convention on Persistent Organic Pollutants came about. And this was signed in 2001 and ratified in 2004. And it banned or restricted 12 POPs, among them PCBs. And it also has criteria for listing of new chemicals in the Stockholm Convention. Persistence, bioaccumulation, toxicity, and long-range transport are one set of criteria, but being found in the Arctic is also an important criteria. Because if you find a chemical in the Arctic that isn't used there, it means it's persistent enough to get there without being broken down, and it's probably undergone long-range transport. So it's P and LRT. And if it's in biota, it's probably bioaccumulative. So after this first report, AMAP continued its work, and 3 more reports were produced on POPs and what we call chemicals of emerging Arctic concern, because we don't know if they're POPs yet. And there were 3 more reports from the Human Health Group following the effects and contaminants, and then also a report on effects in biota. And now they were covering a range of new chemicals: brominated, chlorinated, organophosphorus, flame retardants, perfluorinated compounds, new pesticides, pharmaceuticals, excuse me, personal care products and plasticizers, microplastics, everything we work with here in SETAC is pretty much included there. And to give you some examples then from what came out of there, so this is a spatial trend for penta-BDE, a brominated flame retardant in polar bear. And you can see it's sort of the same kind of picture we've seen before with PCB, with higher levels on the East Greenland side and on Svalbard. And sure enough, when you look at PCB in the same samples, you get almost an identical picture. It's just that the levels of penta are lower than PCB. So this says that penta is coming from the same sources, same source regions. It's undergoing long-range transport, and it's being bioaccumulated, biomagnified. Another chemical that showed up in the Arctic, PFOS. And here it is in blood of women. And this was also kind of an interesting surprise. I think it first showed up in polar bears. And the question was, how is PFOS getting into the Arctic? Because PFOS is totally involatile. So it won't even hop up to the Arctic. But understanding that PFOS was in the Arctic, it was getting there somehow, also led eventually to the discovery that there are precursors to PFOS that break down to PFOS, and those precursors are semi-volatile. So they do fly up and end up in the Arctic. And there are also ocean currents that seem to deliver perfluorinated compounds up to the north. But what's interesting is that you do see slightly higher levels of PFOS on Greenland. And these are women. The men's levels are about 5 to 6 times higher. So PFOS is making it up to the Arctic, and now a lot of other chemicals are making it up to the Arctic. So the effects were studied now, and sure enough, they started to find effects in the top predators, the polar bears and seals and seabirds, showing basically reduced immune function, reduced reproduction, hormone effects on thyroid hormones, for instance, effects on the livers. And these were mostly associated with PCB and dioxin-like PCBs, and to some extent with DDT in birds. In humans, they created cohorts among the indigenous populations and started following them. And they did see now a clear indication of PCB associations with increased ear, lung, and lung infections in Inuit children. Reduced immune systems in children, for instance, T4 or T cell populations were reduced, and lowered antibody response after vaccination, which was strongly correlated with PFOS. And this was very worrying, because this is basically saying that children who have high PFOS levels are not responding to vaccines for childhood diseases properly, which puts them at risk of catching these diseases. Lower birth weights, shorter pregnancies, decreased sperm motility in Greenland men, neurobehavioral effects in highly exposed children on the Faroe Islands, which was also connected to mercury exposure. So these results have then led to listing of 14 more POPs. And actually, I think 2 more have been added in the last couple of weeks. There was a Stockholm Convention meeting a couple of weeks ago. So there are now 28 POPs on this list after, in a sense, these reports of finding them in the Arctic. But 28 POPs, it's good, but we have some major challenges ahead of us. There are large numbers of chemicals in commerce, 80,000, 100,000, depending on who you ask. Recent studies have tried to target and identify those that might have POP-like characteristics and the potential to reach the Arctic, and there are maybe more than 3,000 of these. So, yeah, it's great, Stockholm Convention, 28, but we may have 3,000 of them still out there that we have to worry about. And we also have this problem with what we call regrettable substitution. We banned penta-BDE, the levels are going down, but now we're finding 20 other brominated flame retardants in the Arctic. The same thing with PFOS and a lot of other chemicals. They get banned and new chemicals come back, and they have the same, essentially the similar chemical properties, and that makes them end up in the Arctic. So we talk about history repeating itself. We're just running around in circles. There's a time lag, a long time lag sometimes, from listing on a convention to getting it regulated in the countries that sign that convention to seeing declines in the environment. It's a slow process. And listing on conventions is reactive. The chemicals are already there. It's already a problem. We have to think proactively. We actually have to start thinking of how we prevent chemicals from getting to the Arctic. And if we think about this in the terms of the One Health concept, I've now hopefully shown that, with PCB, the Arctic is interconnected to the rest of the planet. Everything we do in the southern part of the planet will affect the Arctic when it comes to chemicals, if they have the right properties. The Arctic is a sentinel for chemicals and also other environmental issues. It's been good for POPs and new chemicals. We've seen it for mercury. Results from mercury studies have gone into the Minamata Convention, for instance, from the Arctic. Now, climate change. We know now that climate change is happening faster in the Arctic than anywhere else. So it's working as a sentinel for us. So if we want to think in terms of one environment, that the Arctic is part of the globe, and One Health and sustainable societies, that we want to protect ecosystems, living organisms, and humans, not only in the Arctic, but here, we have to think of protecting the Arctic to protect the rest of the planet. Because if we're using things here and they end up in the Arctic, it means that we're being exposed to them too. And this requires a new way of thinking. It means we have to prevent new hazardous chemicals from ever being used in the first place, instead of waiting till we find them in the Arctic. Now, just to end, if you're interested in understanding more environmental issues where the Arctic has been a sentinel, this is a really good book. It's been written, The Changing Arctic Environment. It's written by David Stone. He was the first chair of the AMAP working group, and he's tried to cover a range of issues. And I'd like to acknowledge some of my colleagues. I'm one of the co-leads of the POPs expert group, but I have 3 others, and I'd like to thank Derek Muir, Katrine Voorkamp, and Timo Seppala, my other co-leads. I'd like to thank the hundreds of AMAP scientists who've been involved in these assessments. A lot of you are sitting out there. I see your faces. And I also want to thank the Indigenous hunters and trappers organizations of the circumpolar Arctic, because without them, we wouldn't get samples for these kinds of studies. So, thank you.